Welcome to the deep dive. Recently we spent some time really digging into the physical layer, the
Yeah.
copper cables, the fiber optics, the actual wires that link everything together.
Right, the tangible stuff.
Exactly.
Yeah.
But now we kind of have to shift gears. We need to move up a layer and start talking about the intelligence behind it all. How does the data traveling on those wires actually know where it's supposed to end up?
Yeah, that's the critical question.
It really is. And look, networking can feel like alphabet soup sometimes, right? So many acronyms, so much jargon. It can get overwhelming pretty quickly.
Definitely.
But we're going to cut through that today. Our mission, our deep dive is focused. We are getting right into Ethernet and MAC addresses. We want to understand exactly how these network switches, which are like the essential traffic cops on your network, actually manage to direct data so efficiently.
And to make this really click, we've got a core analogy we'll keep coming back to. I want you to think of a network switch as basically the super efficient mailroom in a huge office building.
Okay, a mailroom. I like that.
Well, yeah. Every single device in that building, your computer, maybe a printer, even a smart fridge these days, has its own unique permanent address. That's the MXC address. And the switch, it's the smart mailroom clerk. Its job is to take the incoming mail, the data frame, and deliver it only to the correct office, the correct recipient.
Without shouting down the hallway or bothering everyone else.
Precisely. No unnecessary noise, just efficient delivery.
Okay, that sets things up nicely. So if the data is the mail, let's talk about the format of that mail first. What exactly is Ethernet? We hear that term all the time.
Right. Ethernet is really the foundation. It's by far the most common technology used for local area networks, LANs, the network in your home or office.
Gotcha.
Its main job is to define two key things at layer 2. First, the structure of the data package, which we call a frame. And second, the rules for how devices actually get permission to send that frame onto the network cable.
And it's been around a while, but it keeps getting faster, doesn't it?
Oh, absolutely. That's key to its success. I mean, it started way back at like 10 megabits per second, which sounds incredibly slow now.
Ancient.
Totally. Then we got 100 megabits, then 1 gigabit, and now 10 gigabits per second. It's pretty common in many places. It's just proven incredibly adaptable and reliable for local networking.
So if Ethernet is like the standard envelope size and postage rules, what's the actual specific address written on that envelope?
Oh, okay. That brings us right to the AMASI address. This is the fundamental unique identifier for network hardware.
And it's fascinating because, as you said, every device, or more accurately, every network interface card, every NIC has one baked right in from the factory.
That's exactly right. MSC stands for Media Access Control Address. It's a 48-bit unique identifier. You've probably seen it if you've ever looked at network settings. It's those 6 pairs of letters and numbers, often separated by colons or dashes, something like a 00.1A, .2B, .3C, .4D, .5E.
And it's not just a random jumble of characters, is it? There's structure there.
Correct. Tells a story. Those 48 bits are split in half. The first 24 bits make up what's called the OUI, the organizationally unique identifier.
OUI.
Yeah, that part identifies the company that made a network card. So Dell has its OUIs, Cisco has theirs, Apple has theirs, and so on. The IEE, a standards body, manages these to make sure they're unique to the manufacturer.
Okay, so the first half says who made it.
Exactly. And the second 24 bits, that's the unique serial number assigned by that specific manufacturer to that specific card. So the combination of the manufacturer's OUI and their unique ID theoretically guarantees that no two network interfaces in the entire world should ever have the same 48-bit MEC address.
A globally unique, permanent hardware ID. Okay, so we have this perfect address. How does this switch, our mailroom clerk, actually use it?
All right, this is where the switch's intelligence really comes into play. As soon as an Ethernet frame arrives at one of the switch's ports, the switch immediately looks inside that frame, specifically at the destination MAC address field.
It reads the to address on the envelope.
Precisely. It figures out where that particular piece of mail is supposed to go.
And this sounds like the absolute key difference, the thing that really separates modern networks from older, maybe less efficient ones.
It absolutely is. This is the aha moment, really. It's what makes a smart switch fundamentally different from an old, dumb hub. You remember hubs?
Vaguely.
Yeah.
They just repeated everything.
Exactly. A hub was like that clueless mailroom worker who just made copies of every letter and blasted them out to every single office. Total chaos, loads of unnecessary traffic, lots of collisions where data packets basically crashed into each other.
Makes sense? Noisy and inefficient.
Very. But a switch, it's intelligent. It reads that destination MSC address and makes a specific decision. It forwards that frame only out of the single port that leads to the intended recipient.
So it keeps the conversation private, just between the sender and the receiver, mostly.
Right. It dramatically cuts down on that background noise and prevents most of those collisions. Much more efficient.
Okay, switches are smart. But they don't just magically know where every single device is connected when you first plug them in, do they? They have to learn the layout of the office building.
Excellent point. Mo, they start with a blank slate. When you power up a brand new switch, its internal map, usually called the MAC address table or sometimes the CAM table or forwarding table, is completely empty.
So it has no idea who is plugged into which port.
None at all. It has to learn dynamically. And the clever part is it learns just by watching the traffic that naturally flows through it.
So every piece of mail that comes in isn't just carrying a message, it's also telling the switch where it came from.
Exactly.
Yeah.
Let's walk through that learning process. It's basically a two-step thing that happens for every frame that arrives.
Okay, step one.
Step one is learn the source MAC. Let's say a frame comes in on port 5. The switch immediately looks at the source MSI address in that frame, the from address. It says, aha, the device with this MAC address is connected to my port 5. And it records that association MAC address plus port number in its table. That's the learning part.
Okay, so it notes down who sent the message and which doorway they used. Got it. Step two.
Step two is look up the destination MAC. Now the switch looks at the destination MAC address in that same frame, the to address. It checks its table. Do I already know which port leads to this destination?
And this is where the efficiency happens, assuming it does now.
Right. If the destination MSC address is in the table, the switch knows exactly which port to use. It forwards the frame at only that specific port. Job done, nice and clean.
But what if it's the first time the switch has heard about that destination? What if that NAC address isn't in the table yet?
Good question. If the destination MAC is unknown, the switch doesn't just drop the frame. It has to figure out where that device is. So it does the only thing it can. It acts a bit like a hub temporarily. It broadcasts or floods that frame out of all its other ports, except the one it came in on.
So it sends it everywhere, hoping the right device will see it.
Exactly. It's basically shouting, hey, is the device with MAC address XYZ out there? I have mail for you. The hope is that the destination device will receive the frame and maybe send a reply, which will then allow the switch to learn its location when that reply comes back in.
Wow, so it's this constant process of learning from the source, looking up the destination, and only flooding when absolutely necessary. It builds its map dynamically.
Precisely. Learn by watching the from address, deliver smartly using the to address. Learn once, forward efficiently many times.
Okay, to really grasp how the switch does this so fast, we probably need to peek inside that envelope, the Ethernet frame itself. What are the key fields the switch actually cares about?
Right, let's look at the frame structure. There are several parts, but the switch is mainly interested in just a couple of key address fields for its core job. There's stuff at the beginning like the preamble and SFD, which are mostly for timing and synchronization.
Getting the receiver ready.
Yeah, basically saying, hey, data is coming. Then, crucially, right near the start, you have the destination MAC address field. 6 bytes long. That's the first thing the switch really looks at for forwarding.
The to address.
Exactly. Right after that comes the source MS address field, another 6 bytes. That's the from address, the one the switch uses to learn and update its MS table.
Got it. Dest first for delivery, source second for learning.
You got it. Then there's usually a type length field, which often tells the switch what kind of data is inside, like maybe it's an IPv4 packet or an IPv6 packet. After that comes the actual data itself, the payload, the message content, which can vary in size. And finally, at the very end, there's a frame check sequence, or FCS. That's for error checking, to make sure the frame didn't get corrupted during transmission.
So the frame is neatly packaged with addresses, the payload, and even error checking. But for the switch's main job, the layer 2 forwarding, it's all about those first 2 address fields.
Primarily, yes. Destination MEC tells it where to send it. Source MA tells it where things are located. Just like a physical envelope, it carries all the essential addressing info right there.
Okay, let's try to make this concrete. Let's run through a quick scenario. Imagine we have 3 computers, say, PC0, PC1, and PC2, and they're all plugged into different ports on the same switch. What happens when PC0 tries to ping PC1 for the very first time? Assume the switch was just turned on, so its MI table is empty.
Okay, great example. PC0 crafts that first ping request inside an Ethernet frame. The source MAC is PC0's, the destination MAC is PC1's. Let's say PC0 is plugged into port 1, PC1 into port 2, and PC2 into port 3.
Right.
So the frame from PC0 arrives at the switch on port 1. Step 1, learn. The switch sees PC0's ME address coming from port 1 and adds that entry to its table. PC0MA is on port 1.
Okay. Table has one entry now.
Correct. Step 2. Look up destination. The switch looks for PC1's MSA address in its table, but the table is still mostly empty. It doesn't know where PC1 is.
So it has to flood.
It has to flood. The switch sends that pin frame out of all other ports, in this case, port 2 connected to PC1 and port 3 connected to PC2.
So even though PC2 wasn't the target, it still gets that first ping frame because the switch didn't know any better yet.
Exactly. Now, PC1 over on port 2 receives the frame, sees his own MSC address in the destination field, and processes the ping request. PC2 on port 3 also receives it, but sees the destination isn't its MSC, so it just ignores it, drops the frame.
Okay, so PC1 gets the message. What happens next?
PC1 needs to send a ping reply back to PC0. So it creates a new frame. Source is PC1's MAC, destination is PC0's MAC. This frame arrives at the switch on port 2.
And the switch learns again.
Yes. Step 1, learn. The switch sees PC1's MAC coming from port 2. It adds that to its table. PC1 MSC is on port 2. Now the table knows about both PC0 and PC1.
Nice. And step 2 for this reply frame.
Look up destination PC0. The switch checks its table. Does it know where PC0 is? Yes. It learned that just a moment ago, PC0 is on port 1. So the switch forwards the reply frame only out of port 1. PC2 on port 3 doesn't see this reply at all.
Perfect. And now, the payoff. What if PC0 sends a second ping to PC1?
Now we see the efficiency. The second ping frame arrives from PC0 on port 1. Learn step. Switch already knows PC0 is on port 1, so maybe it just refreshes a timer. Look up step. Destination is PC1. Switch checks the table. Gingo. It knows PC1 is on port 2.
So no flood this time.
No flood. The switch sends the frame directly and only out of port 2. PC2 is completely undisturbed. That's the learn once, forward smartly principle in action.
That really clarifies it. The initial flood is necessary for discovery, but after that, it's targeted communication.
Exactly. So let's quickly recap the absolute key takeaways for you listening. First, the MSC address, that unique 48-bit hardware identifier burned into every network interface. Second, switch behavior. Unlike hubs, switches dramatically reduce collisions and noise by using those MSC addresses for smart port-specific forwarding. Third, if a destination MSC address is unknown, not in the switches table, the switch must resort to flooding or broadcasting the frame out of all other ports to find the recipient. And fourth, the primary piece of information used for that forwarding decision is always the destination MSC address field within the Ethernet frame.
Excellent summary. So that wraps up our deep dive into the network's mailroom, really getting into the weeds of Ethernet, MA addresses, and how switches learn to direct traffic so effectively. We went from that permanent NavS identity to the dynamic learning that makes switches the efficient heart of the LAN.
We did. And we focused on how that dynamic learning, based on source and mass addresses, is key to the switch building its table. But, that efficiency isn't static. We mentioned the switch has to flood when it doesn't know a destination. We also touched on the fact that these learned entries in the MAC table don't live forever. They have a limited lifetime, they age out, and eventually expire. So that brings up an interesting point to think about. Here's a final thought for you. If a switch's MAC-C table entries are constantly aging out, meaning the switch periodically forgets where devices are and needs to relearn them, potentially by flooding again, what sort of implications might this constant cycle of learning, aging, and relearning have? Particularly thinking about network security and overall traffic performance, especially in really large, busy networks where devices might be connecting, disconnecting, or moving around all the time.
Yeah, that constant churn and the potential need to reflood. Definitely something to chew on regarding performance and maybe even security vulnerabilities in big dynamic environments.
Something to consider.
Absolutely. Well, thank you for joining us on this deep dive into the workings of the network switch.
Keep exploring.